Hi everyone, I'm recording this video to show you the solutions to the sample midterm. Okay, so let's start from the first question. The first question is induction. So what we are trying to prove is we want to show that n factorial is going to be greater than n squared for a large positive n value. So, well, I didn't tell you where starting from which number n factorial is going to be greater than n squared. But if you want to try n equals 4, and then you will see, okay, when n equals 4, and then n factorial is 24, and n squared is 16. So for n as 4, n factorial is higher than n squared already. So what we want to assume, this is the first part. So the first part, we want to find a start point. And then the second part, we want to assume that for a k value, when k is greater than 4, and then we want to assume that, well, k factorial is greater than k squared. So once we don't have to prove that, but starting from this assumption, we want to prove that k plus 1 factorial is going to be greater than k plus 1 squared. So if we assume that it is true, this one is true for a value k greater than 4, and then I can say, okay, for k plus 1, this is also true. So if we start from k equals 4, and because k equals 4 is true, and if we are able to prove this, and then we can show, okay, so when k is 5, it is also true. And then for 6, it is also true. And for 7, it is also true. For any value greater than 4, and then this statement will be true. Okay, so this is my scratching part. And you don't have to show that on your exam paper, but this is my thinking process on how do I solve this. So the first thing I see is, well, one thing I can easily do is I can cancel this k plus 1 here, and then a k plus 1 here. So by canceling k plus 1, this will be k factorial, and this will be k plus 1. So to prove this part, it is equivalent for me to prove k factorial is greater than k plus 1. Okay, so, and then I want to reduce the left a little bit because I know k factorial is greater than k plus 1. This is my hypothesis. So I want to reduce this k factorial to k plus 1, but yet I still want to prove that k squared is greater than k plus 1. Okay, and then I'm going to increase the right side a little bit. I know that k is greater than 1, so I'm going to increase this 1 to k, so I can cancel a k on both sides. So on the left side, I still have k squared, and then on the right side, I have 2k. Okay, so and then if I cancel k on both sides, and then, well, this will reduce to k is greater than 2. Okay, k greater than 2. Is that true? It is definitely true because we are assuming that k is a value greater than 4. So if k is greater than 4, and k is definitely greater than 2. Okay. So for this part, you don't have to show that on your exam paper, but here is the proof. You just have to reverse the thinking process. So you start from, we know that, so this is my solution part. We know k is greater than 4, and because k is greater than 4, we know k is also greater than 2. Okay, and we know k is a positive number. So if we multiply this k on both sides, so this will give me k multiplied by k, that is k squared, and it's greater than 2k. Okay, this is also true. And then if I want to reduce, we want to reduce this k to 1. So this will give me k squared is greater than k plus 1. I'm reducing a k to 1. So I'm making the right side even smaller, so this still holds. And then I want to increase the left side. So I know k squared is already greater than k plus 1, and I also know that k factorial is even greater than k squared. So I'm going to say k factorial is definitely greater than k plus 1. Okay. And after that, I want to multiply k plus 1 on both sides because I know k plus 1 is a positive value. So this will give me k factorial is greater than k plus 1 factorial is greater than k plus 1 squared. And this is exactly what I'm proving. Okay, so this is for the recursion part. And the second one, well, the best case sort. The best case quick sort. So the best case quick sort will be we are super lucky and every round we are picking a perfect pivot. So if we have n values and then after picking a pivot, and then you are likely to have half in on one side and then half in on the other side, and this will be the perfect pivot. And if we keep on being so lucky all the time, and then this will give me the n log n. Okay, and then what's the worst case? The worst case will be, well, if we are picking the largest value or the smallest value as a pivot. So on one side, we have n minus 1 values. On the other side, we have nothing. So this will be the worst case. And then, well, in this case, we are going to end up with doing n square as the running time. So the best case insertion sort. The insertion sort, remember when we did our textbook and my video, we used the pokers, or the cards. So every time we want to expand the sorted portion. So for example, if we have a list of say 1, 2, 5, 6, 8, and 10. Okay, so those are the values I have. And then the philosophy of the insertion sort is, well, I want to grab a value and then I want to insert it to the right place. So if we want to do the low to high, and then this list is already sorted low to high. In this case, well, I'm going to start from the one value as the sorted portion, and then there's nothing to be sorted. And then I want to expand the sorted portion to have two values. So I want to include this 2 into the sorted portion. So I'm trying to insert this 2 into the right place. But guess what? This 2 is already at the right place. So there's no insertion to be done, right? And then how about 5? So when we're trying to add this 5, we want to hold this 5, and then we want to shift the value larger than 5 to the right side. But when we hold this 5 and we see the values in the sorted portion, they are 1 and 2. And 1 and 2, they are both smaller than 5. So 5, we put it down. So in this case, every time we grab a new value, and then we want to figure out what is the right location for the new value, it turns out that there's no shifting to be done, and then we just put it down again. So this turned out to be a linear process, because every time we want to add a new value to the sorted portion, it turns out that this new value is already at the sorted portion, so there's nothing to be done. Okay, so this is the reason that the best insertion will be a linear. And the merge sort. So for the merge sort, and then if you remember, and it's gonna be the case that we first separate a big list into several smaller lists, and then we separate again, and eventually we will all the sublists will be reduced to 1, and then we merge them together. And then we have done a formal analysis of the merge sort. It will be n log n. And for the sequential search, it will be a linear process, and it will be O n. Well, I'm asking the O, so it should be the upper bound. And in the upper bound is, well, the worst case, we have to go through everything, and then we didn't find that, so it will be a linear. And then the binary search. So for the binary search, I'm asking for the big O again. So for the binary search, if you remember the search problem, and then every time we are searching in a sorted list. So if I'm using this sorted list, and then I want to do a binary search for example, 2. Okay, so and then in the binary search, I'm going to find the middle value. So in the middle value, and there are a total of 6, I'm going to find the 3. So index 3 will be this 6. So after finding the binary, and then I want to, after finding the middle point, I want to grab the value on the middle point, and I want to see, well, I'm looking for 2, and the middle value is a 6. So this means 6 and 8, 10. This is the upper half. The upper half, I don't want to search it out, so I'm going to kill the upper half. So every round in the binary search, I can kill half of the search space. So this will give me the log n algorithm. And a primitive step. A primitive step should be a constant time. And how do we represent the constant time? It should be theta 1. And then heapify a node. So if we have a heap, and then when we are doing a heapify, and what's the process? The process should be there is just one value wrong, and then we only want to fix this one value, right? So the worst case is, well, we want to do a heapify that is we have a really small root. We want to drag it all the way down. So for example, if we have a heap like this, and remember, a heap is supposed to be a almost complete tree, right? So, okay, so I think that's enough. And then this is a heap. Okay, so for this heap, and then if we have a super small value here, and then this small value definitely need to drag down to the right location, and then we want to heapify this node. And when we are heapifying this node, and what's the worst case? The worst case is this node will be dragged down here and down here and down here, right? So if we drag this node all the way down toward the longest path possible, and what is that? That is the height of this heap. So, and what is the height of the heap? And it should be log n. So this is the reason we say when we are heapifying a node, the worst case or the upper bound is we take the longest path possible, and that is the height of the heap, which is log n. Okay, so the next one. Well, we are trying to do a sorting, and then this is a selection sort. I'm asking you to write. So for this selection sort, and what we are doing is, let me give you another example. Say we have 5, 2, 10, 3, 15. Okay, so if we have such a list, and what we are trying to do is we want to do a selection sort. So the first part will be, well, we want to find the smallest value, and then I want to put it, I want to swap the smallest value with 5. So I'm going to start from index 1. Well, because I'm doing this as a pseudocode, I want to follow our textbook style. So, well, I have a 5. And let me see if I can make it larger. Okay, so we have 5. And then for this 5, we want to go through all the unsorted portion. And then I want to find the smallest value and then swap it with the first value. So I'm going to swap this 5 and 2. So I'm going to have 5 here and 2 here. So after this part, I have already selected the smallest value. I have already put it into the first value, first location. So in this case, well, this 2 is the sorted portion. And then the unsorted portion is the rest for four values. And after that, I want to visit the second value. And again, I'm trying to select the smallest value from the unsorted portion, and then I want to do a swap. So the smallest unsorted portion is 3. So I want to swap 3 and 5. So it will be like this. And then we say, okay, 2 and 3, they are sorted. So now I want to find the smallest value from the unsorted 3 values. And then I'm going to do another swap. Okay, so this is how I would code this. And I'm going to do a iteration in starting from the I to the length. And then for the smallest, I want to use a value to track where I can find the value, which index I can find the smallest value. And eventually, I want to scan out, after that, I want to scan out the unsorted portion. In the unsorted portion, I want to find the smallest index that I can grab the smallest value from, and eventually I want to do a swap. So every round, I want to do only one swap to guarantee that the smallest value is swapped with the smallest value is swapped to the right location. So the sorted portion is expanded by 1. Okay. So for this part, because every time we are grabbing the smallest value and then put it into the right location, so we are going to sort the values from low to high. And what's the best case? So for the best case, well, we are dealing with a sorted list like this one. So for a sorted list as this one, and then, well, it turns out there's nothing to be done because we don't have to do any swaps. Okay. And another possible answer is there's really no there's no best case because, well, anyhow, well, even though this is I and this the smallest index is also I, we still have to do a swap. So you can say there's the best case is it is pre-sorted, or you say there's no best case here because we are going to have to do one swap anyhow. Okay. Yep. So the next one, recursion. So we are solving a recursion, well, using substitution or iteration. So, for the iteration way, we are separating the working area from by into two parts. And so the left part, I'm doing the solution, and the right part, if I need to know part of the t, and then I want to do the scratching on the right side. So, this is a lot more writing, but this is easier for me, especially you are not so familiar with how to solve recursions. So, I'm doing this iteration way. So t equals 2tn divided by 2 and plus a 5n. So, I don't know what is tn divided by 2, so I'm going to figure out what is tn divided by 2 here. So I'm going to substitute this in and this in using the n divided by 2, and then I figure out, and this is the tn divided by 2 I have. And after that, I want to substitute this tn divided by 2 using the tn divided by 2 I just figured out here. And then I want to massage the result a little bit. And then I find that tn equals 4 tn divided by 4. So it used to be 2 tn divided by 2. Now it is 4 tn divided by 4. And then plus 10n. It used to be 5n. Now it is 10n. Okay, so probably it's not quite enough for me to see the pattern. So I want to reduce that again. So it's another round. And after another round, I find that tn becomes 8tn divided by 8, and then plus 15n. So I kind of see the pattern already. So every time the 8, this value will be doubled. This value and this value, they will both be doubled. And then for this value, it will be increased 5n. Okay, so this is the Python. So eventually I want to write this Python using the value k. So, and you can assume that the base case is t1 equals 1. So when this inside this t, so when this n divided by 2 powers k, this value reaches 1, and that is the base case. So in the base case, we can't reduce the problem even further. We want to solve this problem. So when this n divided by 2 powers k equals 1, this is the case that we have already reached the base case. So we want to stop. And then at this time, k is log 2n. And then we want to substitute this k, and this k with the log 2n, and then we got this one. So this is the non-recursive version of the tn. So we started from here. This is the recursive version of the tn. And by using the iteration way, and then we figure out the non-recursive version of the tn. After that, you have to tell me what is the big O and big omega. So how do I do the big O and big omega? So the long story short, you want to tell me what is the constant value here, and then what is the polynomial here, so that starting from n values greater than 2, and then you will find that tn is always smaller than this. So to prove the big O, you have to provide c multiplied by fn for all n greater than n0, that tn is going to be smaller than c fn. Okay, so you have to tell me what is the c. So in this case, c is 6. You need to tell me which is fn, and the fn is n log n here, right? And then you have to tell me what is the n0, and I say n0 is 2. So starting from n greater than n0 is 2, and then I will find that, c fn is always higher than tn. So I have already found an upper bound of tn, that is 6 n log n. And then I want to drop this c because this c is constant, so I end up with saying, this tn is O n log n algorithm. I have to do another one, which is the lower bound for the omega. So once I'm able to prove that this tn is both O n log n and omega n log n, and eventually I say it is theta n log n. So this is a complete proof of starting from a recursive version of the tn and getting the non-recursive version of the tn, and then prove the big O, prove the big omega, and then I conclude with the big theta. Okay, so the second one, this is a palindrome builder. So we are asking for all the possible palindromes. So I started from a list of palindromes and I'm trying to proceed. And then when the philosophy is, if we have a palindrome x, and then by adding the a on the both sides, so I have the axa. Because x itself is a palindrome, so axa is also a palindrome. But for this question, I want to build all the palindromes using ABC. Okay, so and then I'm going to start from putting the C's. So for the C's, depending on what's the target length, if the target length is odd, I'm going to put the C's as ABC. Or if the target length is an even number, I'm doing AA, BB, and CC. Okay, and then I still need to do a palindrome builder as a recursive function. So every round, I'm gonna grab all the existing palindrome strings, and then grabbing an existing palindrome string, I'm adding A to the both sides, and this will be another palindrome. And then adding B at both sides, it will be another palindrome. So I'm going to use the strategy to keep on expanding the existing palindromes to make sure that I have longer palindromes. But when the current length reaches the target, and this means, I have already reached the target, and inside of my array, there are all the palindromes that has the length as the target, so I'm going to stop. And otherwise, I'm going to do a recursion, because after expanding all the existing palindromes, and then I'm going to increase the current length by 2, because, say, at the beginning, I have the palindromes with the length of 3. And then after I have done this to all the palindromes, and then what I have will be the length 3 plus 2. So all the palindromes I have has the length of 5. So I'm going to keep on expanding that until it reaches the target. Okay, so this is the palindrome builder one, and this is supposed to be a recursive algorithm. So the last part, the master theorem. So the master theorem, the key of solving this question is you want to find for each of the recursive Tn. You gotta tell me what is the A, what is the B, and what is the Fn. So the T is here. Oh, sorry, this A is here, and then B is here, and then the Tn will be this part. So what I can say is A is 2, A is 4, B is 2, and then Fn is n squared. And after that, another thing you want to figure out is what is the n powers log BA. And in this case, n powers log BA is going to give you a n squared. Okay, so n to the log BA is n squared, and Fn is also n squared. What does this mean? This means, n powers log BA and Fn, they grow kind of equally fast. So, and this will give you to the case 2, so which is this variant. So it will give you this variant, and then the theta is going to be n powers log BA, and then multiplied by another log n. So n powers log BA is going to give you theta n squared, and then you are going to have another log n, so it will be n squared log n. Okay, and then the second one. So we are changing the Fn to n cubed. Okay, so n powers log BA is still n squared. So now, Fn versus n to the log BA, which one is faster? And you will find Fn is faster, right? So when Fn is faster, what is that? So Fn is faster, and this will give you the case 3. And for case 3, there is one more thing that we have to prove. That is, we have to show it is possible to find a C value so that A Fn divided by B is smaller than this C Fn. This C can be found. Okay, so let me plug in the numbers. So what is the Fn? So Fn is n cubed, right? So 4, and then n divided by 2 n cubed, and then this equals n cubed and divided by 2. So on the left side, we have the n cubed divided by 2. Can we find a C value so that this can hold? And so we have to find a value that is slightly higher than 1 divided by 2 or 0.5. So can we find that? And the answer is yes, we can find that. And so, well, this c is, well, I'm using this c as the 3/3. And then we, after proving that this c can be found, and then we can conclude by saying this will be a Zeta Fn algorithm. And what is Fn? Fn is n cube. So this is the Zeta Fn algorithm. Okay, and then, well, what's the last one? So the last one, we still have the as4, bs2, and the Fn as n log n, and then n powers log ba is gonna give you n square. So in this case, n square versus Fn, you will find that n powers log ba, that is n square, is higher or faster. So this will give you case 1. So once it gives you case 1, and then you can immediately jump to here and you say, okay, the Tn is going to be Zeta n powers log ba. This will give you Zeta n square. So this is the last question in the sample midterm. Okay, so I hope this video can help you a little bit. And if you have any questions, let me know. Okay.